Okay, I'm going to record this session so that you can review it later on. So once again, to import the file, you need to make sure that the coordinates are, that the unit system is coherent, and once the unit system is coherent with the AutoCAD file, you can import it here, and then you need to check where the location of the node is. So this particular entire thing is located very far away from the origin, so I'm gonna move it to origin. To move it to origin, I'm gonna go to node element, and first of all I'm gonna create a node at the origin. So I go to create nodes and I click apply, and it's gonna create a node at the origin. So now you see this is the origin here, and this is where the elements are, all the elements. So let me zoom in here. Okay, so now I'm going to translate all these nodes to the origin. For that, I'm going to go to node element, translate nodes. I'm going to move all of them. I'll select all of them, and to define the distance, I'm going to use the two nodes. So one, this one, and the other one would be the one on the origin. So I selected one, then I went to zoom fit, and then I went to origin, and I click apply, and entire thing has now moved to the origin, and this is how it looks like from the top. So very simple. Once again, first you import it, making sure that the unit system is okay, then you bring it to the origin, because you know it would be more comfortable to work with the origin. Okay, you can put the origin at the center. So if you want the origin to be at the center line, you can move the origin at the center line by moving the nodes here and there. So this way you will move the bridge. Now for me personally, it is I feel more comfortable working when the bridge longitudinal axis is the x-axis. So I'm gonna rotate these nodes one more time so that I can align them with the x-axis. So I'm just doing this exercise because I am more comfortable with it, but if you don't want to do it, that's up to you. So I'm gonna go to node element, I'll go to rotate, I'll go to move again because I don't want to copy them. I just want to move the entire system from one location to another. The distance, the angle would be -82. So I calculated that distance, and about z-axis, and this would be the point, and I click on apply, and now you can see the bridge has aligned with the x-axis. Okay, so any questions so far? So far it's pretty straightforward, right?
Yeah.
Perfect.
You can't see it yourself, you actually have to calculate it and put an angle.
That's
the only way to do it.
Yeah, I mean you can put an angle, or you can first create an axis here and then project the entire bridge onto that axis, so that you have these two options. Calculating the angle was not too difficult for me because I knew where this line is. I just calculated the angle of this line, and then I made it the y-axis. Okay.
Yep.
Perfect. So now this is what we will start the modeling with. We have more or less the model created for us in this part, but in the curved part we don't have the girders, right? Now to create the girders, it's very simple. So what I'm gonna do is first of all I'm just gonna select this part of the bridge, and I'm gonna make it invisible so that we can just work on one part of the bridge model right now. So I'm just gonna select these two items too, and I'm just gonna go to view inactive. So this makes that part invisible, and now we have only the curved part to work with. Now let's create the girders on the curved part. To create the girders on the curved part, first of all we need these nodes, right? So we have these nodes already with us, but we don't have the interim nodes for other girders. So what I'm going to do is I'm going to divide these lines. So I'm going to go to node element, divide. I'm going to divide them by 5 because we have 6 girders, and now I have more nodes at the location of each girder. So once again, it's something which we are supposed to do because we did not have nodes at those locations. If you had an AutoCAD file which had the connection between the transverse and the girder at this location, we would have a node automatically. The reason why we do not have the girder here, the curved girder or the node, is because the curved line that you have created in AutoCAD, that cannot be imported in a finite element analysis software. So a finite element analysis software imports discrete line. So if that curved line that you have in your AutoCAD, if it were discrete at these points, we would have imported it. So now let's create the girders combining these nodes together. Now the option that we have is create element, but if I use this option, you will see that it will create a straight line between these two nodes, which we do not want. The girder has a certain curvature. So I'm going to use this option. It's called create line elements on curve, and I'm going to use cubic curve by 4 points. So I'm going to tell the program what the 4 points are, and it's going to create the curve for me. And the number of segments will be, you can divide it in as many number of segments as you want. 12 is a comfortable division for this bridge, so that's why I've chosen 12. And then I'm just going to tap on these 4 nodes, and you can see the girder is created. So this way you can create the entire girder. It looks a little cumbersome, but this is the simplest way you can create a curved girder in any finite element analysis software. Okay, so this way you will create the curved girder at all the locations. Is that all right to everybody? Did you guys understand why I used this feature?
Yeah.
Perfect. So is it easy to understand, or like it's difficult to follow so far?
Pretty good.
Okay. Okay, now let's talk about how to create the cross frames. Now once you have created all these girders, you can start creating the cross frames. So to create the cross frames, first of all, what I'm going to do is, if I show you the final model, and if I show you this thing here, let me just zoom in here. So I go to active, and okay, so this is how the cross frames are modeled as of now. The cross sections, once again, they are not proper, but you see here that to create the cross frames, I need more nodes at this location, right? Now to have more nodes, what I'll do is, I'm gonna select this element here, or let's say select the first one, because we want a cross frame there too. So I'm gonna select this one. I'm gonna go to node element, translate. I'm going to translate them by 4 feet in the downward direction, so that I can have more nodes for the cross frames. I will click on apply, and you will see another line of elements and nodes have been created. Then I'm going to select only this part of the model. So I'm going to select only this part of the model, and I'll activate it so that I can see only this part, and it becomes easier to work with. Now I'm gonna go to element, create elements. Now the kind of cross frames that you have, it's a K cross frame, so it needs to be at the center here, but in Midas you can snap at the center of the element, so you don't have to worry about it. Just tap on this node and tap at the center of the element, and this way you can create the cross frames. So right now I'm just creating the line beams or the line trusses for the cross frames, and then I'm going to show you how you can assign the section properties. Now in your drawing file, there was no strut at this location, so I'm just deleting this part. And now one thing that would come to your mind is the cross frames, they are connected at the same web, right? So these two nodes here, the ones that I have highlighted, they should be, the program should know that they belong to the same web. Now how do the program know that? Because this is a grill edge model, all the properties are assigned to the line beam element. So to manually do it, we use the rigid link. So you have two options for that. Either you can use the rigid link or the elastic link of rigid nature. Now here, when you go to elastic link, you can go to rigid, and then you can tap on these two nodes, connecting them together so that the program knows that they belong to the same web. And this way you have modeled the cross frame at one location. Now you can just copy the cross frames at other locations. So select all the cross frames, or before that let's see how we can assign the sections to the cross frame. So I'm just going to select the cross frames again. I'm going to go to view active one more time so that I activate only this part. Now let me define two cross sections, one for the ties and for the struts. So I'm going to go to properties, section properties. I'll go to add, and I'll define the section ID as 2 because one is used for the girder already. So I'll define double angle section, let's say, and I'll define any random cross section. Similarly, I'm going to define one more. So I'm going to go to, let's say this time, let's say angle section, whatever section, and let's define one more. Let's say this is a channel section. I'm just using any random cross section here. So to assign the sections, just select all these ties and then drag and drop the cross section. The bottom chord, drag and drop the cross section. The top chord, drag and drop the cross section. So this way you will model the cross section, and you will assign the cross section to the elements. Now I want to translate this element onto different locations. So I'm going to zoom in here. I'm going to select all the cross frame elements. Now to select them, I have two options. I can double click here and all of them will be selected. So if you double click in the works tree on any cross section, the elements will be selected. And I'm going to select all the nodes also because I want to translate the rigid links that I've created. So I'm selecting all these nodes, and now you can go to node element, translate, and so 21 number of times, whatever number of cross frames you have, you can put it here. And the distance, you must know what is the distance between two cross frames, so you can put it here. Or since I know it from the DXF file, I can just tap on two nodes here, and then I can go to, yeah, you have a question?
Does it work the same way on the curve girder section where it's going to be a different distance along each of the girders?
A little different. Yes, it would be a little different on the curved portion, so I'm gonna tell you how. So
I do have one more question.
Sure.
So, when you put the girders in,
yep,
the node points and the lines for the girders, where are those actually located? Is that the top of the girder?
it's generally at the centroid of the cross section, which is very near, which is just below the top flange.
Okay, so
but you can,
section?
yes, but you can move it. I mean, if you want to move it to some other location, you can do that. But generally, the centroid is the best location.
Okay.
And here, when I copy it, I'll check on the intersect node element so that it intersects all the nodes and elements it finds on the way. And I'm checking on the copy node attribute so that it also copies the elastic link of rigid nature for me. So once I click on apply, you will see that all the cross frames at all those locations have been created and all the rigid links along with them are copied. So not much difficult. It's very easy to copy, right?
Yeah.
Perfect. So we have created the cross frames for the straight part. Now let's see how we can create the cross frames for the curved part. Now the ideology would be exactly same. I'm gonna select them, this line here. I'm gonna copy it down, and then I'm gonna create the cross frames. And then to move them to other locations, I would select it, and this time instead of going to the node element translate, I'm gonna go to node element rotate because they would have a certain angle. I mean, you cannot just translate them in one of the axis. You need some sort of rotation. So here I'm gonna rotate them by So if I know the center of this arc, I can rotate it, and then they would be placed at all these locations. So from the center, whatever angle is subtended between two cross frames, I can put it here. But I mean, if you know that I mean, I'm pretty sure you can obtain that information from the AutoCAD drawings that you will get. But if you don't have them, then you can just create them one by one at these locations as I've done. Okay.
Yes.
So this way you will create the cross frames for the curved portion. Now let's see how we can create the transverse members. To create the transverse members, let me just zoom in at this location. So to create the transverse members, it's very simple. So I'm gonna define one cross section. So I go to let's say section properties, I'll go to add, and I'm gonna define the section. So h would be the depth of the whatever depth your slab has, width would be whatever distance between two nodes you have. So I'm gonna name it as Transverse Deck, and I'll click on OK, and so I have to create it somewhere here, right? So I don't have a node here. What I can do is I can tap on these cross frame elements, and I can go to node element translate. I'm just using these elements so that I can have more at this location, right? So I can translate them by 5 and hit apply. So you have more nodes here, and then I don't have the one connecting these two, so that can be easily created. But before that, I'll change the section properties. So I'm going to select them here. I'm going to drag and drop the transverse section here, and I'm going to create a new one now. So section would be 5, and I'm just going to create it like this. And now I can select all of them. I can go to translate and translate them by 5, whatever number you want to, I mean, whatever the distance is. So let's do it for 20 times for now, and click apply, and it's going to create the deck for you. So this is how you're going to create the transverse members. Okay, so you will create it for all the locations. It's not very difficult. It might seem a little cumbersome at this point of time, but when you start working with it, once you get a hang of it, I'm pretty sure it would be very easy for you to work with. Okay, now let me change the line beam view, and let us see how we can create one of the piers. Okay, so to create the pier, once again, I'm gonna use this line here, because the pier would be directly beneath this line, right? So what I'm gonna do is I'm gonna use this line beam, the bottom struts that I have for the cross frames, and I'm gonna copy them at the location of the pier cap. To do that, once again, I'm gonna go to node element, translate, and whatever the depth, whatever the height of the bearing is, I can translate them by that height. So I'm translating them by 1 feet. I'm assuming the height of the bearing is 1 feet here. I'm gonna click on apply. So I have the new elements created. Now I'm gonna select the newly created elements, and I'm gonna go to view active so that I have the new elements, and I'm gonna define the properties of pier cap onto them. To define the properties of pier cap, I go to, first of all, I define a cross section. I go to section properties, click on add, and I go to solid rectangle. I'm gonna name it as pier cap, and since the bearings would be at the top of the pier cap, I'm gonna change the offset here, and I go to center top, and the depth would be, let's say, 8 feet, and the width is, let's say, 5 feet. So whatever depth and width it has, you can put it here, and you can just drag and drop the new cross section onto it, and if you see it now, it looks like this. So what has happened here is, since I had not defined the cross section, so all the elements that didn't have any cross section have been assigned this pier cap cross section. So to modify it, what I'll do is I'll go to properties, section properties, and I'm just gonna import one cross section. So I'm gonna go to, I just changed the section to steel composite, and I'm just gonna drag and drop the new cross section, So this is how it would look like now. And now I'm going to define one more pier cap cross section. So I'm going to go to properties, section properties, add, and I'm just defining a new one right now. So the reason why that happened was because I did not have the cross section for the pier, for the composite girder. Okay, and now I can just use it, and I can drag and drop the pier cap, and this is how it looks like. So I need to change the offset. Okay, so this is how it looks like. Now let's just activate everything and let us see what do we have and what do we need. So if I go to the line beam view, these cross members that I have here, I need to change the section properties of them. So I can just select all of them and change the section properties. Right now they have been assigned the section property of steel composite, but I can change them in the model. And so let me now just go to this, and just give me a second, please. So I'm going to select the pier cap only here. I go to active, and to model the pier I can use the nodes here, and I can go to node element extrude, and I need a pier cross section, so I'm going to define a pier cross section, and I go to user, whatever the diameter is I can define it here, and I'm going to go to, so I'm using the extrude command to create the pier, which extrudes a node into a line element. So whatever the height of the pier is, I can define it here, and this way the pier cap will be created. So now the pier cap and pier has been created, as you can see here. So it's very simple. I mean, so now let me just open a model that I have already created, and then we'll work from that model. But before that, let me know if you have any questions. Yep.
If say something happens, you want to change how deep the bearings are, like they aren't a foot, they're like a foot and a half or something. I mean, well, a foot and a half's not, it's like 6 inches. How would you just move that, like that line? Is it that easy, or what would be the easiest tool, I guess, to use that?
Oh, okay. Yeah, sure. You can move that anytime you want. So let's say they are not 1 feet, but they are, let's say, 6 inches, as you said. So what I'm going to do is I'm just going to zoom in at this location. I'm going to select all these nodes representing the pier and the pier cap. I'm going to go to sorry, I think I froze the screen. Okay, so I'm just back to the model. What I'm going to do is I'm going to go to the pier cap and the pier location. I'm going to select all these nodes representing the pier and the pier cap, as you can see here, and then I'm going to go to node element, translate, and I'm going to translate it up by 6 inches, which would be 0.5 feet, and I'm going to move them. And once I do this, everything goes up by 6 inches. Okay.
All right.
So it's very easy. I mean, the modifications can be done whenever you want to do it in the model. Any more questions anybody has?
So now the connection between the superstructure and the substructure.
Yep.
Is how are they connected? Do you put in like a link between the two?
Sure. Yeah, that's how they will be connected. So now let me show it to you. So I'm zooming in at that location again, and I'll go to boundary, elastic link, and I'll define a elastic link representing the stiffness of the bearing. So you can put STX, STY, and STZ. So X here would be the local axis of the link. So this is how it would look like. So let me just create it for you. So 1, 2, 3, 4, 5, and 6. So you see here, this bearing has 3 axes. X would be the global Z in the model. So you can just look here and you can make out what stiffness you would want to be put in. So if it is an expansion bearing, only X would work, Y and Z would not. So Y and Z would be 0. And if it is a fixed bearing, then it's going to be XY, STX, STY and STZ. All of them will have certain stiffnesses. Okay. So this is how the deck will be connected to the pier cap. Now there is one more thing. When I go to this location where you have the expansion joint, so what I've done is, this is the pier cap. Let me highlight the pier cap for you. So this is the pier cap here, and then I created additional nodes on the pier cap, and then I connected. So these nodes, let me just highlight those nodes for you. So these nodes, yeah.
One question. The load from the superstructure gets transferred down through the rigid link of the cross frame down into the link that we just created.
That's right. That's right. Yes, that's right. So this way you will obtain the forces in the bearings, and then you can design the bearings by using those forces. So you obtain the forces on the bearings. You can just go to the bearing manufacturer and just tell him this is the force. So you can obtain the appropriate bearing for that. So you can obtain the bearing forces, and for bearing forces you will obtain the bearing force which includes the moving load, because when you perform the moving load analysis on the superstructure, the effect gets transferred to the substructure through the bearings. So the bearings will experience the load due to moving loads. Okay. So now similarly you will create the bearings at all these locations, or what you could have done is you could have so let me just show it to you. So let's say I have created the pier and the pier cap here, and I connected them using the bearings. What I can do is I can transfer the pier cap and the bearings to other locations by copying them. So the way I copied the cross frames, I can copy the pier caps to other location, pier cap and the pier both. So you don't have to worry about creating the pier cap at other locations. You can create it using the copy command, and similarly you can create the pier cap and the pier on the curved portion. So is it all right so far? I mean, do you guys understand what I'm doing here?
Yeah.
More or less, right?
Yeah. One question.
Sure.
For our curve section, New York State wants bottom laterals that sort of intersect midway between the cross frames on the exterior girders. Would we have to create just a rigid link right there also between the bottom lateral and then the actual steel composite girder?
So let me just zoom in here. So are you saying that we need a rigid link between these two locations?
Well, that we would.
Yeah.
Then there's the bottom lateral that goes from the first interior girder to the exterior girder.
Yeah.
And intersects midway between the cross frame.
Yes.
At that point, would we have to have another rigid connection?
No, at this point, no. We wouldn't need it because it is not connect, because the bottom lateral and these ones, they're connected using a gusset plate here, right?
Well,
so,
I'm talking between the two between that cross frame and then the next cross frame, the subsequent cross frame.
Along the length of the girder.
Along the length of the girder, in the lateral longitudinal direction.
Okay, so between this cross frame and this cross frame. Oh, you have a lateral here. Okay, perfect. So if you have it there, then you can model the actual element actually for that. You don't have to create a link for that. You can model the actual element if you have one. The bottom. So I mean,
just draw it.
Yeah. I hope you are talking about something like let's say here to here, something like this, and this, something like this at the bottom.
Well, it meets at the exterior, the bottom flange of the exterior girder, midway between the two cross frames.
Bottom flange of the exterior girder. Okay. Yeah. So
it's almost like a V between the.
I got it this time. So then we would. So you need a node. So you would go to node element, translate it by -4, and then go to create elements, and something like this. I mean, near to this, right? And then you would certainly need a elastic link of rigid nature connecting these two.
Alright.
You would need it, definitely. But the good thing about this is you can just obtain the forces for, for this member here. Okay. Now let's go ahead and talk about how you can define the loads in Midas Civil. So for that, let me open another model in which the loads are not defined, everything else is defined, and then I'm going to show you how you can define the loads. Okay, so this is the model. I have defined all the boundaries required, so let me show you. So if I right click on the supports, you see that all the pier, they have been provided a fixed support at the bottom, and then we have certain links which represent the rigid links and the bearings. To define the loads, first of all, you need to give them names. So you go to load, static load cases, then let's say self weight, and you define the type of self weight to be dead load, then wet concrete load, wet concrete 1, wet concrete 2. Similarly, you can define the barrier loads too. So for self weight, Midas can automatically create the self weight for you. You go to the self weight command here, and specify the self weight as Z-1, click on add, and the self weight will be defined. It will be shown here. And now for the wet concrete load, you would need to apply the wet concrete load individually between the first part and the second part, because they would be constructed in different times. So for that, what I've done here is I have two steel composite sections which are exactly the same, but if you have a different cross section, any other part of the bridge, you can do that. So I have two different cross sections which represent the two parts of the bridge. So I select on the first part, I go to load, and I go to element beam load, then I select wet concrete, and I specify the wet concrete lane load kips per feet, and I click on apply. So as I said, the wet concrete load will be applied only to the girders, the non-composite girders, and that is why I have applied them here. Similarly, I'm going to apply this load to wet to other part. So I'm going to go to I'm going to select the other girders. I double click on the steel composite girder again, the 2-1. I go to element and minus 0.8. The same load will be defined but with a different name, and this way the load has been defined to the curved portion now. So this completes the load definition for wet concrete. You can see how the loads are defined, the two different loads. And if you want to define a barrier load, let's say I want to define a barrier load. So let me first create a name for the barrier load. I'll go to load. I go to static load cases. I give it a name, barrier. The type, once again, you can put like dead load of component in the attachment, let's say. Click on add and select the girder where you want to apply the barrier load. So this is the girder where I want to apply the barrier load. Then I can go to load, element beam loads, and I can so if you want to apply the load with an eccentricity, you can define it here. So whatever eccentricity is, you can define it, and then you can define the barrier load, whatever barrier load you have. So put it under the barrier load case, click apply, and you can see the barrier load is applied like this. So the barrier load would be an eccentric load, and this is how you define an eccentric load. You check on the eccentricity, and then you define the eccentricity based on either local axis of the element or the global XYZ. Okay. So this is how you will define the loads. Now we'll talk about how to model the construction stages briefly. So do you have any questions so far up to what I have done so far?
Okay, so live load later?
Yeah, live load. Let's talk about a live load. Yeah, that's a good question. Actually, I had not defined the live load in your model, so let's just talk about it now. Okay, for live load, would you want to run the live load on the entire bridge, or do you just want to run the live load segregated on two different portions? I guess segregated would be much better, right?
need it. Sure. Okay.
So I guess it would make much more sense if we just apply it on differently on two different portions of the bridge. Although we can apply it on at the same time. So let me just tell you both the approaches, and whatever you think is best for you, you can just choose it. Okay.
Yeah.
So let me open another project here. Just give me a second. Or let's first talk about construction stage modeling, and then let's talk about moving loads, because there's a certain part which is overlapping and I don't want to confuse you. So let's first talk about the construction stage modeling. Okay. So for construction stages, it's very simple to model construction stages in Midas Civil. Once you have completed the geometric modeling and the load definition and the boundary definition, so there are three things that you have to do. The first thing is you need to define the construction stages. So let's say I want to define the first construction stage as substructure, then girders, the first set of girders, and then the wet concrete on those girders, the stage for applying the wet concrete load, and then the deck becomes composite. So part 1 composite, and then you go to install the girders 2. Oops. So I go to girders 2, then I go to wet concrete 2, and then I go to part 2 becomes composite. So this completes the construction of the entire bridge. So first of all, you defined all the construction stages. Now the second thing is, when you go to a construction stage, wherever you have to activate, you cannot activate individual elements. You need to activate a group of elements as well as boundaries and loads. So for that, what you will do is you will go to the groups tab here and you will define different groups. So you can see for boundaries I have defined 10 different groups. So the first group is cross frame links. Now when I define the elastic link of rigid nature to connect the two nodes here, which represent that it's the same part of the web, I used the type as rigid and then I tapped on 2 nodes. Now I want to activate this cross frame in a particular construction stage, and when the cross frame is activated, I want to tell the program that it belongs to the same web, right? So for that, what I'll do is, when I'm creating the cross frame link, I'm gonna put it in a boundary group. So I can give it any name and I can put it in this particular boundary group, so that when I activate the cross frame, I also activate this group. So similarly, when you create the rigid links, you will put them in the group. When you create the bearings, you will put them in the group so that you can activate them. So the bearings or the whatever links that you're using in the program, they have to be activated explicitly other than the elements, and that's why you're putting them in the group. Similarly, in order to activate the load, you will use the load groups. To define the load groups, you go here, right click and go to new, and you define the load groups. And when you are assigning the loads onto different elements, here you would have noticed the load group. So you can, when you are assigning wet concrete 1, you can put it under wet concrete 1, and this way you can assign the loads under the load group, right? So that's why when you define the load under the load group, you can activate them in the construction stage. The same is right for the other elements like girders and stuff. So if I want to activate the girder in one of the construction stages, I will define a structure group, put the girders in that structure group, and then I'll activate it. So first of all, I'm gonna create a new group for piers. So I'm gonna name it as Pier, let's say, and I'm gonna select all the piers in the model and I'll put them here. Now to select the piers, I can use the selection tool, or I can go to the works tree and I can select pier and pier cap. So this way all the piers and pier caps are selected. They appear in red. They are highlighted. And then I will just go to the groups tab. From the works tab, I'll go to the groups tab and I'll drag and drop the group pier. Similarly, I'll define girder 1 and I'm going to put the girder 1 elements into the group girder. So do you have any questions so far?
No.
Perfect. Similarly, I'll do the same thing for cross frames. So I'm going to select the cross frames and I'm going to put them in the group. So let me select all the cross frame elements right now. So I've selected all the cross frame elements. I'll go to group. I'll define a new group named cross frame 1. So the cross frames should be activated first for the first part of the bridge and then for the curved part of the bridge. So what I'm going to do is I'm going to define two groups, cross frame 1 and cross frame 2. And first let me just activate all the cross frames here. Now I'll put the straight part cross frames into cross frame 1 and the curved part cross frames into cross frames 2. Okay. And now let's define the construction stage. So right now I'll just define the construction stage for substructure and till wet concrete. So I'll go to define construction stage. In substructure, I'm going to activate the pier element with a certain age. The age is important because you can also perform the time dependent material analysis with it. So I'm activating pier. In the boundary, I'm going to activate all the pier supports. So I'm going to activate all the pier supports that I have created. And in the I'm going to activate the self-weight. So I'm activating the self-weight in this construction stage. Now I go to the construction stage and all the piers are activated along with the boundaries. Now I can go to the next construction stage, girder 1, and I will activate the element girder 1. I'll activate the cross frame 1. In the boundary, I'm going to activate the cross frame links. It is important to activate the cross frame links. And now the girders will be connected to the pier cap using the bearings. So I'm going to activate the bearings for part 1. And if I see it now, you will see this is the stage 1. And then in the next stage, the girder appears along with the cross frame. Now you would notice that on the top of the girder, you have the deck also in the longitudinal direction, which comes with the composite section. So now how to fix that? To fix it, it's easy. You will go to this button here, which is composite section for construction stage. You will go to add and then you will select the stage when the girder 1 appears, and you will tell the program when the part 1 and part 2 appears. So I'm gonna select part 1, material would be steel, and for part 2 the material would be concrete with density equal to 0, and the active stage for part 1 would be girder 1, and the deck appears in the part 1 composite. So I'm going to define part 1 composite and certain age to the concrete, and I'll click OK here, and then I go to girder 1, and now you will see only steel appears and the deck does not appear on the top of it. But when you go to the part 1 composite, you will see that now the deck also appears on the top of the girders. So this way you can model the different construction stages in Midas Civil, and that is exactly how I have modeled the construction stages. Now in the stage when the deck appears on the top of the girder, we also need to activate the transverse elements. For that, let me activate all the transverse elements here, and I'll select the transverse element for the straight part. I'll put them in the group trans deck 1, and I'll drag and drop this group, and similarly I'll put the group trans deck 2 and I'll put them in this group. And now I go to the stage where the part 1 becomes composite, and I go to element trans deck 1 and I'm gonna activate it. So when you go to this stage, so stage 1 substructure, stage 2 girder 1s are installed along with the cross frames, and then the wet concrete load is applied and the section becomes composite, and you can see the transverse members also appear. So this way you model the construction stages in Midas Civil. I hope it is clear. I'm pretty sure that you must be finding it a little difficult at this point of time, but once you start working with it, I'm sure you will pick it up very quickly. Do you have any questions so far? Let's
So
now talk
transverse-
about moving loads. Yeah.
Transverse is just pretty much like a placeholder then, sort of. And
The transfers is, I'm sorry?
transverse sections are just sort of like a placeholder.
Yeah, I mean, they are required so that the bridge has a transverse stiffness that is contributed by the deck. So when the deck appears in the longitudinal direction, it should also have the stiffness in the transverse direction, and that's why we have the deck members in the transverse direction.
Okay.
Okay. Now let's talk about moving loads. Yeah, do you have any more questions?
They were good.
Okay, so for the moving loads, I'll go to load option and I'll go to moving load, and here I'm going to select the code as H12RFT. Then I can define the traffic line lanes. So for defining the traffic lane, let's go to define lane 1. Now you can see we have two types of vehicular load distribution called cross beam and lane element. So for the grill edge members, we use cross beam. So in the cross beam elements, all the deck members should be put in. So the deck members would be trans deck 1 or trans deck 2. So once again, if you want to perform the moving load analysis only for, segregated for part 1 and part 2, you can select trans deck 1. So you can name it as lane 1 straight, and then you can define lane 1 curved. And this way you can perform the analysis, or you can define one lane in which the vehicle moves from one end of the bridge to another end. So let's talk about both of them. So lane 1 straight, and then you just define it on the trans deck 1, and to define the actual lane you click on two nodes, the starting and the ending, and this way you click on this node and you click on the other node here. So this way the elements are selected, you can click on OK, and the lane will be defined like this. So this way you can define the lane. Similarly, you can define other lanes. Now let's see how we can define the lane on the curved part of the bridge. So to define the lane on the curved part, I'll name it as lane 1 curved, and I'll put it on the cross beams trans deck 2, and this time I cannot just click on two nodes because they are not on the straight line. So I'm going to use the picking option, and I'm going to select these girders here. So I'm just going to select all the girders in this direction, in this actually, and then I can ask the program to apply the lane. So to select them, we have this feature. So you can, for the curved bridge especially, we have created this feature where you can select it using a polygon, and then you can just put these numbers in the number tab, and the lane will be defined accordingly. So you can see here the lane is defined. Now if you were to define a lane from one end of the bridge to another end of the bridge, considering both the straight and the curved parts, then you need another structure group which combines the trans deck 1 and trans deck 2. So I name it as entire deck, let's say, and then I put the transverse deck 1 and 2 in this group, and then when I define a new lane, I can just name it as lane 1 entire bridge, and I can put it on the cross beam group entire deck. So this way I'll define the lane for the entire bridge. Now the only thing which is remaining is how to define the vehicle. So to define the vehicle, go to vehicles, and you can define a standard truck with any type of dynamic allowance, and you can also define your own user defined vehicles by going into user defined. And so I have defined the vehicle here. Let's define the tandem 2 with a certain dynamic allowance, and then you can create a moving load case, or you can create a vehicle class where you can combine the truck and the tandem together. So I'm naming it as HL93, and then you can create a moving load case where you can combine the lanes with the truck or the vehicle class. So this way you can combine the lanes. So you can define like whatever number of lanes, 3 or 4 you have in the bridge, you can define all 4 of them, and then you can put them in the moving load case along with the vehicle class. So this is how you will define the moving load cases in, or the moving load data in Midas Civil. Is that all right?
When you define the lane, I thought you just put it over the girder.
Yeah.
Should it be like the limits of the travel way? So like we have a sidewalk and
Okay.
the HL93 truck is permitted to mount the sidewalk. So it's not necessarily going to be just over a girder.
Sure. Then you can use the eccentricity option, and then you can create a lane eccentric to the girder. So you just use girder as a reference. The load will always be transferred from the deck elements to the girder. Okay. So
So since our bridge is wide enough to have 4 lanes, do we define all 4 lanes?
yes,
And then, okay.
you define all the 4 lanes, and then the program will put the vehicle onto 1 lane, use 1.2 multiple presence factor, then 2 lanes, it will load 2 lanes, it will apply multiple presence factor as 1, then similarly it will do the analysis. So it does all the permutation and combinations automatically, and it gives you the voice out of 2.
So for New York State has a permit truck which has different lane loading criteria,
Sure.
where it actually wants like 1 permit truck in 1 lane, and then you load the rest with HL93. So is
Sure.
that, do we just send a different moving load case?
Yes, in that moving load case, what I'll do is I will go to moving load case, and here you can see we have sub load cases. So in 1 lane I'm gonna put permit truck, in another lane I'm gonna put some other vehicle, and then in the rest of the 2 lanes I'm gonna put HL93, and then the program, I'll use the combined option. The program will combine the results of all of them to give me the worst effect.
Okay, so you just give it one scenario and it'll move it to find the worst case?
Exactly. So I can, I mean, generally when you're working on bridges which have railways and vehicle loads too, you can use this effect and you can combine them together. So you can use it for permit too. So you can define the permit truck, and then you can, on 1 lane you can use permit, and then on the rest of the 3 lanes you can use HL93 or stuff like that. So is that all right?
Oh.
Does it move it within the lane? Like move the truck within the lane to give you the worst?
Well, generally, I mean, the program would keep the vehicle axle at the centroid of the lane. I mean, at the center of the lane, right? The axle center would be the center of the lane. So if you want to consider the transverse placement of the vehicle, you can manually create that lane where you want to put in, and then you can perform the moving load analysis based on that lane. Because generally, if I ask the program to move it transversely automatically, it's going to take a lot of time to run the analysis. I mean, we don't have that feature in the software, but if you use any software that does it transversely, it takes a little longer time. So that's why we do not have this feature. And the engineers want to have the liberty to define the lanes according to them. So that's why, I mean, nobody requested it so far. That's why we don't have it in this software. So let me take up your questions now. I think so. I have a question here, link between MicroStation and Midas, DXF input and output. So if you want to import anything, I've already shown you how you can import it from MicroStation or DX AutoCAD. If you want to export it, you can just select the model or part of the model, and you can go to File, Export, and then you can export it for AutoCAD, DXF, MicroStation. And so you can use Midas to create your steel framing plans too. Now, another question, possibility of line grid analysis. I did not understand your question. Please, can you please shed some light on line grid analysis for me?
Line girder. Yeah, line girder. Yeah, I mistyped. Line girder analysis?
Oh, is it line grade or line girder?
Line girder is a mistype.
Oh, okay, then line girder analysis, I believe I have already covered that. And so we have talked about the bottom laterals connect.
No.
Yeah.
As far as applying live load, we have
Instead of doing a grillage analysis, is there a way to just do a single line girder analysis?
Yeah.
Where you specify the spacing and then calculate the distribution factors based on ASHTO?
Well, the distribution factor method we do not have in our software, because if you are performing refined analysis using a grill edge model, then you wouldn't need that distribution factor, because that distribution factor is generally created using the grill edge approach. So if you are performing the grill edge analysis, then you would not need it. But if you still want to do that kind of analysis, then you can, when you define the vehicle here, you can actually define, when you define the moving load case, if you are just modeling one girder, you can define the scale factor which represent the distribution factor, and this way you can do the one girder analysis, single girder analysis.
All right.
And I think I've talked about, let me talk about steel code check later. And question number 3D, in case of bottom laterals connections, call out rigid elastic link. Yes, I have used rigid elastic links. Questions regarding model development, measuring tool rotation, moving portions of structures around an axis. So for that, I have already demonstrated to you the translate tool and the rotate tool. So we have all these tools that you can use. And live load applications, sidewalk loading, truck placement, different type of truck loading, separate models, etc. So you can do all sorts of moving load analysis with different trucks or sidewalk loads at the same time in one model. You don't need separate models for that. You can create several moving load cases, and then you can ask the program to create an envelope for that. So if I have 10, let's say I have 5 different type of moving load cases, I can just go to result combinations, and then I can ask the program to create an envelope of all those loads for me. So you don't have to manually check which load case is more severe. You can ask the program to do it. Now talking about seismic analysis. So question number 3G is where I am. So seismic analysis, Midas can do all sorts of seismic analysis like response spectrum analysis or time history analysis. So we can have another session in which I can talk more in details about those type of analysis, because I think the first step for you would be to either study the model or run the static analysis on this model with moving load analysis and do the preliminary design, and then we can have another session in which we'll talk about seismic design. But Midas supports all sorts of seismic design. And now, do you have any other questions?
That's fine with the seismic. I was more looking for the how we should define our connection between the superstructure and the substructure, and then the substructure to the foundation.
Okay.
Ahead for putting together a seismic analysis, so we can actually run the seismic analysis later on.
Sure. So connections I have already talked about, but we can also model the actual foundation under the bridge. So if you want to model the foundation, you can model the pile cap and the piles below it. So let me quickly show it to you how you can do it. So I'm just going to model one foundation system. So to do that, what I'll do is, first of all, I'm going to use these nodes here. I'm going to translate it to create more nodes. So I'm going to go to node translate, and in the y direction, let's say by 4 feet. It's going to be a little higher than 4 feet. Let's say 8 feet is fine. So I'm going to define it as 8 feet, and then similarly in this direction, I'm going to put it as -8. And then I'm going to create a line element, and I'll use that line element to create the pile cap, because it's going to be a shell element. So I'm going to use create element. I'll define any random cross section to this. Let's say 11. And the property is concrete. So I'm just going to create these elements. And now to make a much finer mesh, I'm going to divide this element into, let's say, 2 parts. And similarly, I'm going to divide this element into 2 parts, and these 2 elements into 3 parts each. So basically, and then let me just actually activate this part of the bridge model itself. So I go to view active, and to create the pile cap, I'm going to use this line. I'm going to go to node element extrude. I'm going to extrude the line element to planar element, and I'm going to define whatever thickness it has, and in the x direction, let's say 3 feet, 5 number of times, and similarly 3 feet 5 number of times. So this creates the pile cap for me. To create the piles, what I'll do is I'm gonna select the nodes at the location of the piles. So wherever the piles are located, I'm gonna select these nodes. So here it is, and then once again I can use the extrude command. So I go to node element, extrude, and node to line element. I'm going to define a new cross section for the pile. So let's say it's a circular pile with 2 feet diameter, and I'm going to put the cross section as 10, the grade of concrete as 5000. So let's say it is 30 feet, so -3 10 times, and once I click on apply, it's going to create the piles for me. So this is how the piles are modeled. Now to apply the soil supports to the piles, what I'll do is I'm going to select all the pile elements here, and I'm going to ask the program to create the pile springs for me. So I go to integral brace support, I'll select the pile springs, and I specify the soil parameter. So specify the ground level, the pile diameter, the coefficient of subgrade reaction, and all these geotechnical values that you can obtain from, I guess, Charlie Sims in your office, and then it's going to create the soil springs for you. So this way you can actually model the entire foundation system, and the good thing about this modeling is that when you perform the moving load analysis, it will actually give you the forces on the pile cap and the piles considering the moving loads too. Is that alright?
Yeah.
Perfect. Now let's talk about steel code check. As of now in our software, we do not provide the composite girder code check as per Astral RFT, but we are in the process of developing it, and it would be out, I think, in March. It would be out March or April, and then you can do the automated design for the steel composite section. But as of now, we do support the steel girder design as per Astral RFT 2012, as well as you can do the reinforced concrete design. The Pier design, Pier cap design can be done using reinforced concrete design tool. So these kind of designs can be done in Midas. You can do the cross frame design using the steel design, but when it comes to girder design, it is a steel girder and the concrete deck on the top of it. So you need to do the composite design, but that is not supported as of now, but we are in the process of developing that. Okay, so this is all I wanted to share with you today, and I will supply you the model so that you can play with it and see for yourself how the different elements are created. But I would personally recommend all of you to start with the DXF file that Dan sent me, and then try to create the model by yourself, because this is your first project, and I know that you would have a little difficulty in working with Midas for their first project, but once you complete this project, I'm sure you would understand all the modeling concepts in Midas.
Did you record this session too?
I did record this session, and I'm gonna